So welcome everyone to my talk, an introduction to fuzzing and a direct application to the real world. So a little teaser. Today you will learn what this fuzzy little cute bunny has to do with this hacked iPhone here. So for the contents, this is kind of a two-parter. So the first part, don't worry, it will release right after the first part, in contrast to Dune. So the first part is I will talk a bit about fuzzing, give an introduction, how it works, what it is. And then in the second part, I will present how I used fuzzing in my thesis to find bugs in the iPhone bootloader. All right, I was already introduced, so I'll keep this short. Yes, this is me. I finished my Bachelor already, starting my Master sometime soonish, probably. Yeah, I've been a member for Flagbot for long, and I've been also the president for long, so yeah. What is Flagbot exactly? You already mentioned some of it. So for those of you who don't know, CTFs are basically team-based cybersecurity competitions. So together in a team, Flagbot or organizers, we solve cybersecurity challenges. And yeah, we've been ranked first place in Switzerland 2019, 2020. We usually play, almost every weekend we play CTFs, and that just means we come together at ETH and try to get some points and score some flags. And we have weekly meetings on Monday, at the moment hybrid, so at 9 p.m., at 7 p.m. Over Zoom and in person in CAB H52. So they're open to everyone who wants to join, who wants to learn more about CTFs, who wants to play with us. Just come, we help beginners there, we maybe introduce new topics, stuff like that. So it's definitely worth it. Yeah, he also talked about organizers. So yeah, it's a joint team between Flagbot, Polyglots from the EPFL, the Crown, and Secret Club. And for larger events, we team up. We're currently ranked 7th worldwide, and we have multiple big wins, such as, yeah, we were the best European team at VIScon finals, and we placed first at Tencent CTF a few weeks ago. So that's cool. But yeah, anyways, let's continue on with some motivation, right? Imagine you're a company. For now, I've redacted the name. It might be big, thousands of employees across the world. It might be very small, 2 people working in a garage, designing the modern computer, whatever. The problem is, of course, like all software, your software has flaws. Actually, many of them, security issues, right? The press has a field day. You have a 0 day there, a 0 day there. That's not a good look for you. So, of course, you want to fix those flaws. And the problem is, on the one hand, there's just too many of them, right? And I mean, another issue is that security experts, they cost a lot, right? You don't want to pay millions of dollars for like 5 people to find bugs for you, right? That's just too much money. You can't afford that, even if you have thousands of employees. So what do? Well, why not use, like we all start to use in modern software development, automation, right? Why don't we use automation to find vulnerabilities? And I don't mean this kind of modern automation where you use AI or just statistics. And yeah, so what do we use instead for discovering vulnerabilities? We use something called fuzzing. And this is a very broad term, actually, and you will see in a bit what it actually all encompasses. But the gist behind it is it helps you automatically find vulnerabilities. It can run unsupervised, so that's great, or mostly unsupervised. And it has a great track record. So it's becoming more and more popular because of its great track record. For example, Go, I don't know, maybe some of you know the language, Go. In the next version, they have native fuzzing support. So just like you would write the unit test, you would then write the fuzz test. So this is really, really becoming important and popular. And you also have something called OSS Fuzz, which is by Google, where they provide fuzzing, infrastructure, tooling, and all that kind of stuff through open source projects. And as of this February, they have found over 26,000 security bugs. So this is quite a lot, right? So you see, it really works well. But what is it? Well, almost this. Not quite. You will get this joke in a bit. Don't worry. So what's the basic idea behind fuzzing? You have this kind of basic loop where, first of all, you generate potentially random input. Just generate some input. You run your program with the input, right? Okay, it runs, and then you see what it does, what the program does with the input. And the idea behind it is, well, if your program crashes, the security researcher is happy, right? He has found a bug, great. You are not happy, and the customer is especially unhappy because the program crashed. So you probably want to avoid that. And meaning that if you observe any crashes while running your program, well, it probably has bugs you want to fix. And important here to note that it doesn't necessarily mean that those bugs are security vulnerabilities, and I will get into that a bit more later. But we'll see how we can make it so that it's more likely to actually mean that there's a security vulnerability there. All right, so you know the basic idea. Let's talk about how we can categorize fuzzing, because I think this is interesting and important to know. And so, as I said, there's a very broad spectrum that fuzzing encompasses. But there's, I think, these three important ways of categorizing it. And the first one isn't that interesting, which is why I have it just on this slide. So basically, how do you generate this input? And you can either mutate previous input, so you just have a previous image file, you mutate it, or you can generate from scratch. Usually, modern tools use mutation, maybe some generation from scratch. It's also not really that important, I think. And then the other two, which I think are more important, is how aware is the fuzzer of the input structure and the application structure. So what does that mean? Well, for the input structure, as I said, if you fuzz, the input can be anything, really anything. So you don't just have text, it can be images, image files, it can be network messages, it can be keyboard input, right? If I mash my keyboard, you could consider that fuzzing. And in the beginning, like 1980, it was considered fuzzing. If you just mash your keyboard and the program crashes, well, it's not good, right? You want to avoid that. And usually, however, when you have a program, the input should have a certain structure, right? So, for example, if you have an image editor, the structure would be a PNG file, right? At the beginning, probably, it has some information. This PNG has this width, this height, then some information about the data, then the data itself, right? So this is the structure, right? First this, then this, then this. And this is almost all input should have structure, because if your input doesn't have structure and your program parses it correctly, well, you probably have generated some kind of AI. So I would check that out. Anyways, so yeah, we have structure for our input, and this structure also helps the program distinguish valid from invalid input. And why do we care about a valid input now when fuzzing? I said you want to crash your program, so you would probably want invalid input, right? I mean, that sounds logical. Invalid input probably crashes the program. Well, the thing is, you want your fuzzer to toe this very fine line between valid and invalid inputs, because if the input is too invalid, the program will just error out very quickly, right? It will just say, this file is invalid in the first few code blocks, and it's just say invalid, done. And if it's too valid, of course, it will just parse it correctly and not crash. So you want to have this somewhat invalid input maybe, but that's still valid enough so that it reaches all paths, or at least most paths of your program. So this is why we actually want to have why it would make sense to have some awareness of the input structure. And so we have these two definitions here, which is, the first is a smart fuzzer, which is basically a smart fuzzer means, it has pre-existing knowledge of the input structure, and it can use that to more or better mutate or generate new inputs, right? So for example, if you have a grammar-based fuzzer, it means it has the grammar of a language, for example. So if you have the Python grammar, which describes how the Python language works, and then it can use that to generate almost or valid Python code. And then a dumb fuzzer, of course, is the opposite. It just does nothing. Well, it does no such thing. And it also has its advantages. It's easier to operate. It can be faster, stuff like that. So usually you have a mix between those two as well. And yeah, exactly. All right. So now application structure. The basic idea behind fuzzing we have nowadays is that fuzzing is effective if you have high coverage. Because the idea is, well, if you have low coverage, meaning only small parts of your program are actually reached while fuzzing, well, then there might be bugs hiding in the parts that are not reached, right? So you want high coverage to almost reach everything, so that hopefully all the bugs should have been triggered. Of course, this is in theory. In practice, you might still not trigger bugs, but yeah, in theory. So we have these two opposite ends of the spectrum. We have a black box fuzzer. Basically, it just considers your binary and black box. It just feeds data in, has two outputs, either it crashes or it doesn't. That's all it does. The interesting thing is this can be very effective. We have used this tactic in CTF before. 5 lines of bash, and we found a bug. So it can actually work, even if this sounds very stupid and very simple, right? It actually works. And it's very fast, easy to parallelize, so that's great. And of course, as I said, 5 lines of bash, it can be very quick to set up. And it has been used for quite effective bug finding before. On the opposite end, you have a white box fuzzer, and this is fully aware of every nook and cranny of your program, right? So it uses high heavyweight analysis to actually figure out, okay, to be able to reach this part of the program, I need to mutate my input like this, stuff like that. And an example what a white box fuzzer might do is it has symbolic execution or taint analysis, if you've heard of it before, otherwise just ignore it, I guess. Yeah, and because of this heavyweight analysis, it is slow, and it's difficult to scale, so that's why it's not so great and why it might not be used that often. It also, of course, requires a high degree of customization for every program, so you can't just expect it to be 5 lines of bash to get it to run. Right, and what do we usually use? Well, usually we use actually a middle ground. We use something called the gray box fuzzer, which uses instrumentation, lightweight instrumentation, to learn information about the program structure on the fly, and then actually use that learned information to fuzz more effectively. And so what this usually means is you trace basic block transitions. For those of you who have had compiler design, you know what that means. Or just imagine you have standard code coverage, right? You know, okay, this line is covered, then I know, yeah, I have some information about what my input does. Also, some recent advancements, just FYI, I think this is kind of interesting, is that we can start to use sanitizers to actually gain even more information about where we should fuzz. And it's almost as fast and scalable as black box fuzzing. The only overhead is the instrumentation, which is usually lightweight, so you maybe have like 10, 20%, depending on your binary performance decrease. So yeah, it's quite good. And yeah, most popular by far. And of course, it supports most program configurations. So yeah, a middle ground, and it works really well. All right, so now I want to talk a bit about how this fuzzing works in a bit more detail. This is not supposed to be a tutorial, but like just what I learned while doing this myself and what I think is interesting here. So first of all, you have to choose a fuzzer. Look for language support. As I said, Go will support it in the next release, so I would then use the built-in tools. Otherwise, I would recommend something called AFL++, because it supports many configurations, it's continuously updated, and there's also some simple grammar-based stuff in there. You have advanced instrumentation support even. It's pretty cool. And so here in the next few slides, I will assume that we are using AFL++. So what is it? It's based on American Fuzzy Lop, and now you will get the joke because this is also the name of the fuzzy bunny I showed before. You will often hear in the internet that AFL is bad, it's outdated, you shouldn't use it, it doesn't have the modern things in there. This is why AFL++ exists. So this is very up to date, it has the modern stuff in it from papers, stuff like that. So don't feel threatened by those comments, you can use AFL++ just fine, it works great. It is also the most well-known coverage guided fuzzer. So you see this GUI here. It's very famous, so famous indeed that it was used as the scoreboard at DEFCON finals. So it is very famous. And yeah, uses execution tracing, it can also use comparison coverage, and even sometimes it can use simple constraint solving to mutate the input, to figure out, oh, okay, if I take this path, to take this path, I need to mutate this in my input. So it's very cool. And so here's a schematic overview of how it works. On the one hand, you have something called seed inputs. They initialize the input queue, and this is basically all the inputs that AFL++ thinks are interesting. They do something to the program. It might be that it reaches further into the program. It might be it crashes, just something that it finds interesting. And then AFL++ takes the next part of the input queue. It's really a queue, so it takes the next element of the queue, called input here. So let's say it has the content input. Then it mutates it a bunch, so in Q or in pot or an U input, right? So these are mutations on the input. And then for every mutated input, it runs your binary or your program, right? You need to compile this from source code, of course, and then you can fuzz it. And let's say we have a function here that's called fuzzme that we want to fuzz. And yeah, then when it's ran, it actually gives feedback, right? It gives feedback about the coverage reached, and it gives feedback about whether it crashed or not. All right, so what are those seed inputs? I think they're interesting to look at because there's a few things you have to pay attention here. Yeah, they provide the basis for mutation, and there's some very important considerations. The smaller, the better. Why is that? Well, let's imagine you have a file that's 10 bytes and a file that's 1,000 bytes. And in both files, if you flip a single bit, so it's very specific, but just a single bit is enough to make the program crash, right? So this is the bug. But it's only a single bit out of 10 bytes or 1,000 bytes. Well, the chances of you flipping the correct bit in the 10 bytes file is way larger, right? So you want to keep the test cases small. Even if the chance of getting the bug scales linearly, so stays the same with the larger input, it's still better to have a smaller input because it's faster, right? I mean, if the program has to load 10,000 bytes, it's much slower than if it just has to load 10 bytes. So this is something to keep in mind. You also don't want to feed it crashing inputs. AFL++ is very good in helping you, so it will just complain and will not let you continue. Don't worry too much about it. There's very detailed reasons why you don't want to do this, but they take a lot of time to explain. So I'll just gloss over. Just remember, don't do that. And you also want to have a wide range. So don't just use 50 vacation pictures shot with the same camera. It doesn't really help. It just makes fuzzing actually slower and wastes compute time. You really want to have completely orthogonal test cases in the best case. Because otherwise, well, it can just use the first one and mutate it, and it will probably get to the second one very quickly. So use very orthogonal test cases, don't make them overlap too much. Right, now you want to set up fuzzing. So you want to select good target functions, right? You don't want to fuzz a function that just returns true. I mean, you're not going to find a bug there. So you want to find something that's probably complex, does complex parsing, or has many corner cases, stuff like that. And it also often makes sense to only throw fuzzing at parts of your program, right? If you have heavy setup routines, you don't want to fuzz those because those are A, probably doing always the same thing, and B, are just slow. So yeah, think about that. And then you also probably want to remove difficult to fuzz features because checksums, I mean, if the fuzzer could with random mutation find the, calculate the checksum, I think we have a bigger problem than security bugs or even cryptography, right? Because then it would just break crypto with random input. It's probably a very bad thing. And so what will happen, is, of course, if you have this stuff, is almost all your input will be rejected, right? Because checksum is invalid, crypto is invalid. So you want to remove that. Usually, I mean, those crypto operations are also slow. I mean, calculating a hash is way, way slower than just doing some parsing stuff. So that's why you also want to remove it entirely and not just always return true, maybe. So yeah, this is something to also keep in mind. All right, now onto compiling your program. This is not just, well, you use your normal compiler to compile it. You actually need to use the one that's provided by the fuzzer because it then adds that necessary instrumentation. The fuzzer, especially AFL++, has good documentation on how to do it. So yeah. And you also want to add something called sanitizers. I mentioned it before. These are what are also important because they help to actually crash when some common security issues occur. For example, you have ASAN, stands for Address Sanitizer, and basically it will then help to crash when you have an overflow of a buffer or when you have a use of the free, stuff like that. It will then actually crash. And this means that you will then actually increase the chances of when you crash to have a vulnerability. You still need to triage them, of course, but it makes it much more likely that if you're crashing, you probably have found a bug, or even a security bug then. All right, so on to the last topic in the introduction. Let's say you're a government agency, some military org, and oh no, you lost access to the source code of your program, right? It's totally not that we have this binary lying around from, I don't know, some country we want to attack. We lost the source code. This is really bad, right? So what can you do? AFL++ is good at that. It supports binary-only fuzzing. So that means you don't even have to compile your binary. You just give it the application, basically, and you can then use QEMU, a CPU emulator, to emulate it and add instrumentation on the fly. So this is cool. It can also be used to fuzz cross-architecture. So, for example, you can fuzz ARM stuff. So you have in your phone an ARM chip, right? And you can fuzz that on a normal x86 server, for example. You can also do something called statically rewriting. So there's, for example, the RetroWrite, which is pretty cool, developed by EPFL, which basically just takes the binary and then statically adds instrumentation. So in the compiled binary, it adds instrumentation. This is very difficult, and it's still an active area of research, but it's, of course, then much faster because you don't have to emulate anything. You're actually still running the binary normally. And it theoretically is should be as fast as if you would have compiled it from source with instrumentation. Right. So now you have glimpsed into the world of fuzzing. Let's talk about this now. Fuzzing the iPhone bootloader. And so some of you might have now guessed that these opening quotes were actually about the iPhone. And yeah, iPhone security major talking point in the press, has been, continues to be, of course. And for now, just trust me, you will see in a bit why. But what is very important for the security guarantees that the iPhone, well, at least supposedly gives you, is the bootloader. And of course, this logically means that vulnerabilities in that bootloader are highly sought after. So I thought to myself, well, that's great. Let's find a bug, right? Then we get 5 million or something paid from some shady government org, and I have a yacht and can go on with my life. The problem is, of course, I don't have many researchers under me. I have 0 researchers under me. I don't have a budget to buy like a few hundred people like the NSA does. So what can I do? Well, of course, your answer now should be, oh, why don't you use fuzzing? I mean, it's free. It's easy to set up. Well, maybe you'll see in a bit, and it's great. It works. So, well, this was the goal of my thesis. Let's try and apply state-of-the-art fuzzing to the iPhone bootloader. Before we get to that, a bit of background. So some of you might be like, okay, what the fuck is a bootloader? And bootloader is basically, it's usually the very first piece of code that runs on your phone. I mean, almost any hardware, but think of your phone. And then it is basically responsible for initializing the hardware and setting up everything so that your main OS, so your main operating system can actually run. You can go on TikTok and drown in the endless stream of content. So yeah, that's what the job of the bootloader is, to make you suffer. No, just kidding. So yeah, on the iPhone, this bootloader consists of multiple stages, and these stages together form something, well, or they form a secure boot chain. And how that works is basically you have the first stage, it loads the second stage from disk, verifies that, this is authorized to run on your device, authorized by Apple, and if it's authorized, it then runs the next stage, and the next stage does the same thing, and so on and so on. And this, of course, then forms this kind of chain, right? So we have this diagram here which shows it. So you power on your iPhone. What happens first is the first stage called SecureROM runs, right? And then in normal operation, it will load iBoot from disk. And on disk, these stages are stored in something called IMG4. You don't really have to understand what it is, just that I will talk about IMG4, and this is just the format these things are stored in on disk. And so it gets loaded. Is it authorized by Apple? Yes, it is. Great. Let's execute it. Then iBoot runs. It looks at the kernel. Kernel is just your operating system. You can think of it as that. It loads it from disk. Is it authorized by Apple? Great. Let's run it. Done. Now, what happens, you might say, if this is not authorized by Apple? So it might be corrupted. It might be missing. A bunch of things could happen. Then SecureROM enters something called DFU, or Device Firmware Upgrade Mode. And this is a USB protocol where you can plug in your device to your laptop, and then iTunes uploads a recovery image for here. So IBSS, it uploads that via this DFU protocol, via USB, and it then starts the recovery process. You can also enter this mode if you press some combination of buttons on your phone. Right. So now you know how that works. Let's talk about attacking this. So usually when we think about fuzzing, we first develop a threat model so we can see where it might be effective to fuzz. And so we also should ask ourselves, why is it even good, or why is it interesting to attack SecureROM? So I'll be attacking the first stage here. I mean, the headlines before were all talking about flaws in Safari, in iMessage, stuff like that. I mean, this is at the other end of the chain, right? We are talking about the first link in the chain. Why is it interesting? Well, an exploit here is very, very powerful. And for example, getting code execution in the kernel, trivial, you can just load your own. It also can lead to larger attack surface for the secure enclave processor, which is a secure coprocessor on your phone that encrypts user data, stores fingerprint information, Apple Pay wallets, stuff like that. So if you have a larger attack surface there, and this was actually shown in previous talks, you can then steal fingerprint data, steal Apple Key wallets, all that good stuff. Well, good for the attacker, not good for you and me. But yeah. It can also not be patched, so don't worry about burning a 0-day if you have one for SecureROM. It cannot be patched, so yeah, don't have to worry about that, can just use it. And it might actually lead to persistence. So these are great things. Now, we have these two distinct threat models, I feel like. We have on the one hand the physical attacker. They have access to your phone, they have it in their hand, they connect it to a laptop, and then they can either send malformed USB messages or malformed image4 files via this DFU protocol. And if an attacker just has root on the device, could be physical, is most likely remote, really the only thing they can do to interface with SecureROM is write a corrupted image4 file to disk, right? And then hopefully the SecureROM will parse it weirdly and crash or something. And so because physical access is more powerful, we actually assume this in the following slides. So here's a diagram. So you have the attacker here with physical access. They control an image4 file sent via DFU, or they control the USB messages directly. So these could be 2 points where we want to attack or fuzz, right? And then here, the attacker with root access, they just control the file on disk and this. All right. So the next challenge, we have to build a fuzzable binary. Of course, you say, well, I mean, you just take the source code, compile it, with instrumentation, with sanitization, done. Well, unfortunately, it is not that easy. We have source code. Well, it's leaked. It's from 2016, so very outdated. It's incomplete. So even if I wanted to compile the outdated source code, it wouldn't actually compile. So that's, yeah, not really possible. So what do we have? We have a binary blob without symbols, meaning we have no function names, no variable names, nothing. And we don't even have an idea where the text and data is. So you don't even know where in this binary text, so code or data is. So that's bad. It's designed for Apple processors, which at the moment are still ARM. So the ARM instruction set, maybe you've heard of it. All phones use it. But the problem is ARM sometimes has implementation-defined stuff. So Apple or Microsoft, or whoever develops, Qualcomm, for example, develops ARM chips, can just say whatever, this instruction does this. And Apple can say something different, Qualcomm can say something different, right? This is bad. And then also, it wants to run on bare metal, meaning it really is the first thing that executes, so it wants to have access to specific hardware devices. It wants to have access to the MMU. It wants to really have all this very, very privileged access that you don't normally have. Right, and usually fuzzers are assuming this is you have a program that runs in user space, meaning it doesn't have all this privileged access. So we have developed multiple solutions, and these all work together. So the first solution is static analysis. So loading the binary in a decompiler gives you something like this, right? This is an example function. Of course, you have no idea what any of these functions do. You have no idea what any of this does, what any of these fields are. Great. So, and you might have seen before in the figure with the schematic overview of the fuzzing or the threat model that I actually already named some functions, right? For example, I think image load, right? Of course, this was done after I've already done static analysis. So with static analysis, we can then do this. So this is the same function again, but now I've renamed all the functions according to what they actually do, and probably their original names in source code. And this is almost equivalent to what the source code is actually like. And so with this, we have a lot better time with the binary. And so what does it help with? Well, of course, we now have actual symbols. We know where text data is, stuff like that. Designed for Apple processors, it helps somewhat there because we can infer certain things about implementation-defined stuff via context. So because of static analysis, we know, oh, okay, this function does this, and here it reads an implementation-defined register. Well, it probably does something like this implementation-defined register. And for bare metal, it also helps because we can infer context about what certain hardware devices might be doing, or what SecureROM expects that they might be doing. Right, then the next solution is binary patching. So we patch stuff in the binary, and you might think, oh, this is actually quite few binary patches. And indeed, this is almost all of the patches we have to do for the binary. So it's not actually much. And for example, what we do is we patch in our own USB driver, so we can fuzz more effectively, and more on that later. But yeah, so this is all we do. I think the design of the patching is quite interesting. So if you are interested in something like this, do look at the thesis. I think it's very cool. So what does it help with? Well, it doesn't really help with symbols or anything like that. It does help, of course, with the implementation-defined stuff, because we can completely patch out the instructions if we don't need them. We can patch them with our own custom implementation of the instructions in normal C code, stuff like that. So yeah, it basically fixes that problem. And it also somewhat helps with bare metal, right? We can patch in our own driver. Right. So the last solution, which again works together with all of the other ones, is, well, instead of fuzzing SecureROM directly, why don't we just write a normal C program, right? With a main function, with printf available, all that stuff, and then just use SecureROM as a library. So link it in, This, of course, is not as trivial as it sounds. It's very complicated and stuff like that. But we basically link it in as a library and then just call functions of it. And you might be thinking, well, why? I mean, this doesn't sound like what you normally would do for fuzzing. And I agree, this is not what you would normally do. But it works very well for a few reasons. First of all, we can use existing fuzzers without any modifications to the fuzzers, right? Because at the end of the day, now our binary is just a normal Linux application. I can run it normally, perfectly fine. It doesn't need anything special. And so that also means we can use any of the existing fuzzers without modifications. Furthermore, this actually works, right? You could be saying, well, does it really work? I mean, you said, oh, it needs all this bare metal stuff. Does it really work? Yes, because the functions that we call and that are interesting to fuzz don't need any of that bare metal. I mean, parsing those image4 files doesn't need to handle MMU stuff or anything like that. So it really does work fine, perfectly fine. And we can, of course, fuzz selectively, and it also allows way more easier debugging because we can just run it normally. We can debug it like you would normally debug a Linux application, right? So this really helps a lot. Right, so what does it fix? Binary blob without symbols. Yes, it helps there because we now actually know we have the sections correctly in the binary, stuff like that. Doesn't really help here. It does help with the bare metal stuff, right? Because now it's a normal Linux binary. We don't have to have basically a full system emulator to actually run it. It really does just run under Linux. So this helps a lot here. All right. Now let's talk about fuzzing this image4 part here. So we are here. We want to fuzz this thing here. How does the schematic look like? This is actually quite simple, right? We have our target. So this is the binary, the Linux binary I compiled. Here is SecureROM linked into the binary as a library. And basically, AFL++ generates some input. It passes it to the fuzzme function. And the fuzzme function basically just immediately calls image load. Very simple. Really, this is all it does. Maybe some debug printfs, but this is all it does. So does it work? Well, I ran it for a week. And I didn't really find any interesting crashes, unfortunately. I did find some interesting results with respect to speed, though. So let's quickly talk about that. The fuzzing speed was actually much lower than expected. You even see it here on the right. We get it. It's slow, right? It's because it's so slow. It was kind of mocking me, but okay, let's analyze why this happens. So one issue is that the target is restarted every run. Which means, of course, if you think about it, well, Photoshop, if I start up Photoshop, it takes like 3 years. So, of course, if I restart this, it also should probably take some long time. So, yeah, this is very slow, of course, it's restarting it for every single input. And another thing is something called POC. POC is on ARM, a new technique where basically, in simple terms, you use cryptography to protect pointers, because if an attacker then overwrites a pointer, the chip can then actually verify whether the signature is still valid of the pointer. And of course, if an attacker overwrites it, unless they broke the cryptography, it will not be valid. And so it can then crash. And this is used to protect against buffer overflow attacks, stuff like that. And of course, in QEMU, this is implemented in software, which, as you know, crypto in software, very slow. So, of course, this also contributes here quite a lot, actually. It's very interesting that it really does affect it a lot. So what do we do? Well, just tell QEMU, ignore those spec instructions. Nobody cares. I mean, we're here to find bugs, not be prevented from finding them. So, yeah, just ignore them. And what we also use is something called persistent mode for supposedly better performance. So what's that? Well, basically, the idea behind it is AFL creates this fake loop. So we have the fuzzme function, right? And instead of when we return from the function, actually return to main, or when we call exit in the function, actually exit the program, just return to the beginning of the function and give it the new input, right? And this then basically has this fake loop where it constantly just calls fuzzme. And this, of course, should be a lot faster in theory, right? Because we are not restarting the target anymore. We're just running the function in a loop. Well, the fuzzing is actually slower now. Okay, this is not great. So why is that the case? Well, the issue is that AFL++ tries to be smart and thinks, okay, I want to have a snapshot of all memory at the beginning, and then I restore it on every iteration so that it's easier to reproduce actual crashing inputs, right? Because then you don't have to worry about, oh, maybe I first need to do this step and then this step and then this step, right? Because they all depend on each other. That's why it restores the memory. Problem is I have a lot of writable memory pages, so like multiple megabytes are mem copied at the beginning of every loop iteration, which is of course very slow. So yeah, what do we do? Well, we patch AFL++ to basically only snapshot certain page regions, which we need, otherwise it doesn't work. The problem is it's still too slow because we still need a lot of pages. So what do we do? Well, luckily there is a kernel module available that does copy and write snapshotting. So basically only if a page is actually written to, it is then restored. Otherwise, it doesn't do that. And that's, of course, then very efficient because while we have to snapshot a large range of pages, we only write to a very small subset. So this is great. The problem is this kernel module was broken, really, really broken. It had security bugs in there. It didn't work. It didn't compile even. So we first had to fix all of that. But afterwards, it worked really well. So you see here, we have in blue, and this is logarithmic. So we have in blue at the beginning the speed. So it's like 100 executions per second, going down to, as you saw, like 10, 20 often. And then here for red, we have with persistent mode, where it's slower, like half as slow. And then or half as fast. And then here in green, we have the kernel using persistent mode and the kernel module. And you see, it's really, really fast, right? I mean, this is I think the max I saw was like 22,000 executions per second, which is a speed up of, I don't know, I think like 400 times or something. So really, really, really helps a lot. All right. So now let's go into the more interesting part, USB fuzzing. So the schematic is a bit more complicated here. So bear with me. So we have the input, right? And then fuzz me again. And then it has a few more arrows. Why is that? Well, I would have been very surprised to find out that you only need a single USB message to actually make your phone crash, right? That would be very bad for Apple. Not for me, of course, but for Apple, very bad. So what I do instead is I take this large input, which is actually just a sequence of bytes, right? I take it and I split it up into a lot, much smaller sequence of bytes. And then in each of these, I send to SecureROM as a USB message. So I sent the first small part, I sent the second small part, and so on. And this is what these arrows indicate. Don't worry about the part below here. It's not really important for the rest. Just, yeah, so you have an idea. All right, and before I talk about the USB fuzzing now, I want to first introduce some important things for this. So a short refresher on the heap. Basically, this is the mechanism for dynamic memory allocation. You probably should know this if you've been to Sysproc, but again, I will give you a short refresher here. It's used by most programs, even though, well, at least some form of heap is used, even if you might not directly recognize it, because yeah, sometimes in languages you have automatic memory management, so it does it in the background for you. So the important functions here are malloc. You give it a number, this is how many bytes you want. And it then gives you a pointer to the start of a buffer that has that many bytes available for you to do everything you want with it, right? This is the basic idea. And then you have the second important function, which is free. You give it the pointer you got from malloc, and it will then release this memory that it allocated for you to be used elsewhere. And so after you have called free on a pointer, you should really not use it anymore because, yeah, very bad things happen. And so, yeah, this is needed, of course, because manual memory management, you need to call free on every pointer you allocate yourself. All right. So now the next thing I want to introduce is something called checkmate. What is checkmate? It is a previously found vulnerability in SecureROM. And what it abuses or exploits is something called the use of the free. So you allocate, let's say you allocate a pointer to a buffer, then you free the buffer, but the pointer is still there. You use the pointer for whatever reason, and then, of course, this buffer is free. I said before, you should really not use this pointer anymore, but people still use it. That's called a use of the free. Makes sense, right? The name is just use of the free. Right, and before I did my thesis, publicly, it was clearly known that iPhone 4S to the iPhone X or iPhone 10 were exhibiting this bug. It was not entirely clear whether the iPhone 10s and 11 also exhibited this bug. So the goal here is, well, let's find this bug with fuzzing. I mean, right? Fuzzing is here to find bugs. This is a bug. Let's find it. Right. The problem, well, the fuzzer does not find any crashes. Damn it. Yeah, it's a bit surprising, right? I mean, it's a bug. Fuzzing should find bug. Why doesn't it work? So there might be a few reasons. First of all, the fuzzing doesn't work correctly. This would be very bad for me, right? I mean, I spent all this time and it doesn't work great. I might be fuzzing the wrong parts. I said we're replacing the USB driver. If the bug is in the USB driver, of course, it will not be triggered because we're replacing it. Still not as bad as the previous option, but still not great. Then the third option is the fuzzing finds the bug but does not crash. What does that exactly mean? Well, the problem is you might have bugs that you can trigger, right? You trigger the actual bug, but it doesn't really do anything. It doesn't crash. And of course, then the fuzzer doesn't find it because it looks for crashes. It doesn't look for bugs specifically. So, and this is actually what happens. Why does it happen? The problem is if you don't do something called heap Feng Shui, which basically means you do a bunch of allocations, a bunch of frees, so that the heap is in a very specific state, the buffer will be allocated at the same place after the free, which means, well, there's again a buffer there, so okay, you have technically a use of the free, but it doesn't really help you because, well, there is again space there for you to use. So it doesn't really do anything. And this issue might not be exclusive to SecureROM. And so you can have it with other allocators, other kinds of bugs. So what did we do? Well, we basically created a custom allocator to kind of find this anyways with fuzzing. And so let me introduce fuzzing enabling thread safe allocator, or FETA for short. And let's see what it does. So it's a drop-in replacement for any code using malloc or free. Basically, it just overrides these functions. It's thread safe, as the name implies. And it can detect and crash on heap overflows or use of the frees. And so what's the basic idea? We want to crash as soon as the bug happens, right? You don't want to crash 2 years down the line because, well, it's going to be difficult to figure out when the bug actually occurred if it's way too late. And so I thought about this and I was like, I remember from sysproc, right, if you access a page of memory that is not mapped in your process, you crash, right? So what do? Well, we isolate every heap chunk on its own set of memory pages. And that will actually work quite well. So let's see an example here. We initialize the heap. And then let's allocate some chunk. And as you see here, anything that has this dark green border around it is mapped. And anything that doesn't have this dark green border around it is unmapped, meaning if you access any of this memory here, crash immediately. And so what happens? Okay, we have the pointer to the chunk here. So we have this chunk is hex 100 bytes. And so if you overflow by even just 1 byte, well, we access something that's not mapped, crash. Perfect. This is exactly how we want it to work. So let's continue. We allocate the second chunk, we free the chunk, and as you see here, all of this is unmapped. So if we access anything here, so we have a use of the free, we crash immediately as well. Great. So the results. Well, using this, we can actually find checkmate. And even the time to exposure is very short, which is interesting because, I mean, I know that Apple does fuzzing as well of their SecureROM, and I mean this bug has been present for 6 years now or more. So it was kind of also surprising to see it. I mean, I think the shortest time I had was like 20 minutes from start to finish, like from starting to finding the bug. So it was very surprising. It also confirms that checkmate is still present on iPhone 11 because we used iPhone 11. It just cannot be exploited. And so I think FETA raises some interesting questions. Because, I mean, we used a different allocator and we could find now bugs that were previously hidden in the fuzzer. So maybe we can design other libraries that help with finding bugs with fuzzers. So, for example, we could expand FETA to detect memory leaks. The only reason why we can't exploit the bug on iPhone 11 and iPhone XS is because we would need a memory leak to do this heap Feng Shui, right? But we could also think about other types of libraries, right? A threading library could be interesting to, maybe there's a design for a threading library that allows us to really trigger race conditions with fuzzes, right? Because race conditions are very, very hard to trigger, even if you manually want to trigger them. So having a specialized design for threading libraries might be very interesting. All right, so let's wrap it up. First of all, fuzzing is becoming more and more important, and the setup can be very quick or at least pretty quick, and you have very modern tooling, so no more excuses. Start using it, especially if you're programming in Go. I mean, it's basically free. Just instead of writing a unit test, you now also write the fuzz test. Of course, even though I said this a bit cheekily in my opening, it does not actually replace security engineers. You need people designing the fuzzing, you need people setting up the fuzzing, you need people triaging the bugs found by fuzzing. You should probably still want to have security people looking for bugs separately. You want to have people looking at 0 days in the wild, stuff like that. So it doesn't really replace those people. It just augments their abilities like we have with unit tests and QA, right? You don't just throw out your QA team just because you added some unit tests. Right. Now, on the second part, we have the iPhone bootloader fuzzing. It was actually successful, right? It confirmed the existence of checkmate, and I think FETA actually performs really well, and it's quite interesting what we could maybe look at in the future of that. Right. Here are some useful links. The most important one is this here, so flagbot.ch/material, because there you have these slides available. Then you can click on these links and don't have to actually type them out. Especially this one, you probably will mess up one of the letters. So just go to flagbot.ch/material and download the slides. You can just click and great, you have the actual links. All right. Now this would be it. Do you have any questions for me? Yes.
You said that all of this was part of your bachelor thesis, right?
Yes.
Where can we find that?
That's here. So source code. The source code here includes also like a link to the PDF of the thesis. Yes, I can actually go back here to this slide now. Yes. Any other questions?
Okay, so just what are kind of the resources, the servers that you need to do your iPhone fuzzing?
For this, depends a bit. I mean, you can really do this on like your home machine, or I wouldn't really do it on your main home machine, but like a single, I was running most of it on just a single PC at home that was running Linux. Yeah. I mean, what Google uses is like a cluster fuzz. They have like hundreds of servers, but they also support, of course, provide fuzzing for hundreds of projects. So yeah, it really already can work quite well if you just have like a few cores. I do recommend you don't run it on your main machine because fuzzing processes really want all of your CPU, so you don't want to have anything competing for resources. You also probably want to turn off all the Spectre meltdown mitigations and stuff because those just slow you down, right? Who needs security? So yeah, and that's another reason why you don't want to do that on your main machine, right? But yeah, you can just use a single PC that will already work quite well. Yes, I think. It is exploitable on, I think, 5S till 10, but then not exploitable on 10S and 11. Yeah. Unfortunate, but I mean, some might be happy that it's not exploitable, right? Because it can also be, of course, a security issue with if your phone is exploitable. Right. Any more questions?
I think most people are still processing what they just.
Yeah, I'm sorry. It was a lot of content.
They get all the questions when they arrive at home. So I think your mail and the Flagbot team is all linked well, so they can all send the questions they get when they.
Of course, I'm happy to answer any remaining questions you have, or if you want to read the thesis and then have questions, I'm happily available at my email address, which is at the beginning. So yeah, open the slides, I guess, and then go to the beginning, and there you should have a nice mail link.
So I think if there are no questions, I'll hand you over your thank you gift. It's your second talk, so you already know how this goes.
Thank you.
There's your small welcome. And yeah, check out his thesis. It's 50 pages, I think, around 50 pages.
Exactly. I wasn't allowed to write more.
It's a great read. It's all on GitHub.
Yeah, it's a lightweight read. You know, you can read it for bedtime, then you fall asleep easier.
Has a lot of pictures.
Yeah.
For those of you who aren't in a hurry, there will be some sandwiches on Politerrasse. Yeah, I saw some of you look up right now because they heard food. You can just go to the Politerrasse and there will be a queue, and you can get some sandwiches and then go on to the next talk. And then I thank Leo wholeheartedly for his talk. And I hope we see more fuzzing action in the future now that you have all these things set up, so it doesn't go to waste.
Very fair.